welcome to the UKCCSRC meeting in Sheffield with the storage parallel session, looking at what happens to CO2 once it goes into the rocks underground. I'm Stuart Haszeldine from the University of Edinburgh, and I have the pleasure of chairing this for the next hour. We've got 4 speakers, all of whom were funded for at least part of their work by UKCCSRC flexible awards during the course of the grant that we're just finishing off. And so in that sense, people are reporting back to the meeting about what they did with the money, or their students did with the money. So first speaker is Sam Krevor from Imperial College in the big city of London. Was attracted to Imperial with the promise, presumably, of some of the world's best equipment, which is what they actually have now, I think, of micro-scale investigations of CO2 saturation in pore space. And Sam is a reader in carbon sequestration studies and is interested in going from the very, very small scale to the very, very large scale. So I'll hand over to Sam to talk.
Okay, great. Well, thanks very much for that, Stuart. Thanks, everybody, for joining today. And thanks to the UKCCSRC for organizing, as ever, such a fantastic bi-yearly meeting. It's great, as many people have said, to be here in person with you all. So just giving a brief summary of some of the activity from the core research activity to do with the subsurface that I've been involved with through the UKCCS Research Centre. I'll be talking about 2 things. The 2 types of modeling, really, of what happens to CO2 when we inject it underground. So firstly, the type of modeling that we should be thinking about with regards to scaling up CO2 storage, and then the type of modeling that we should be thinking about when we're injecting CO2 into individual reservoir sites. So starting at the very large scale, we, through the UKCCS Research Centre, started thinking about how the subsurface should be represented in the types of large-scale systems models that the results of which you see here from the Intergovernmental Panel on Climate Change, but there are others. The CCSA presented the outcome of their models, and the UK government makes use of energy systems models to analyze how climate change mitigation can be achieved within some sort of economical boundary. And with regards to CO2 storage, you see figures that are at the global scale that are along the lines of what you see here. To achieve less than 2 degrees C of warming across the globe, a number of simulations combining technology and economic growth says that around 10 gigatons on average, CO2 needs to be injected underground every year by mid-century. And that's a tremendous scale up. And you see these kinds of figures repeated in a large number of independent modeling efforts. So when you look into this and say, well, that's a lot, it's an important question to ask how the subsurface is being represented, and also how it should be represented in this type of modeling. So if we look at the figures, okay, so here just showing a little bit more granular. Again, these types of numbers have been specified for a number of countries or regions around the world. The Committee on Climate Change here in the UK has provided roadmaps reaching out to mid-century. The European Commission, through their Green Planet for All working papers, have specified what this might look like for the entirety of continental Europe. And if we put these figures in context of where we are now, we see the following. So the vertical axis of this graph is injection rate estimated of CO2 annually since around 1996, when Sleipner began. And there are varying ways to put these numbers together. But in terms of the capture capacity, that's usually what's reported. You see on a logarithmic scale a fairly steady average rate of growth when you're looking across kind of 20 to 30 year timescales. That represents about 7% annual growth in capture capacity over that time. And so actually, when we took a look at this, we thought that was pretty good, given the kind of patchwork of incentives and what seems to me a consistently negative narrative around the progress of CCS. Actually, what we see here is fairly steady annual growth for this technology, and at a rate that is commendable. But if we put this in context of what is implied to be achieved by mid-century or earlier, for example, in these global scenarios synthesized by the IPCC, you see that extremely high rates of growth need to be achieved to hit even kind of the lower range of the targets that these systems models say are needed to achieve these mitigation targets. So 10% growth has been achieved, is being achieved by a number of technologies today. 20% growth is not something that you generally see sustained over multi-decadal time periods. So you can say, yeah, sure, early technologies have extremely high rates of growth, but that's sustained for kind of 5 years, maybe 10 years. And when you're looking at 20, 30, 40 years of growth, these kinds of averages are too high. And so what that says is that there's something about the way the subsurface is being represented here that's not quite capturing the dynamics of what's possible in the 2050 targets and earlier in these large-scale scenarios are probably implausibly high. So I think that probably creates a large part of the narrative, the negative narrative around CCS. So you can see assessments from organizations like the International Energy Agency that ask the question, well, how is CCS doing? And the benchmark has become the outcome of these energy systems models. And because they're using implausibly high rates of growth, the outcome of those assessments generally identify that CCS is not on track. But if you just look at the types of models and the type of growth that is happening with CCS, and think about reasonably what growth might look like. In other words, if we approach this problem from the subsurface and looking up, you get a much more positive outlook. So if we just continue the rate of growth that we see today to the end of the century, for example, what you find is that CO2 storage is able, at that relatively modest rate of growth, achieve the mitigation targets for a whole range of the 1.5 degree and 2 degree C scenarios. Just to say the rate of growth that we're seeing now isn't that bad. And it is on track to play a significant role in climate change mitigation. And of course, you can look at what rates of growth you'd need to achieve to obtain more ambitious targets. But putting it in that context provides a more realistic trajectory. You can do other things like take historical data. Here's work from Phil Ringrose, just looking at the growth of injection wells and production wells in different regions, hydrocarbon regions of the world, in Norway, the Gulf of Mexico, and showing that the rate of construction of these wells over recent history has actually achieved the kinds of growth rates we need to, again, hit some of the longer term climate change mitigation targets. So they're largely consistent, whether you're looking at economic growth, construction and development specific to the subsurface. And all of that says that if we just integrate our understanding of the subsurface, both in the types of models that are appropriate and the history of how it's been developed, we can identify a much more positive and I'd argue factually correct narrative around how CCS is doing in the role and the opportunity it has to play. Okay. The other thing that we can do is very rapidly identify more achievable or more realistic targets in the context of both growth rate that's historically precedented and constrained by the storage resources that have been assessed to be available. I won't go into the details of how we do all that, but here I've put the combined plans of the European Union and the UK on a number of trajectories of these models that are, again, suitable for representation of subsurface constrained development. What we have on the vertical axis is the storage resource in the region, and you can very rapidly identify, for example, an ultra-conservative scenario in which we've said, well, let's depend on rates of growth sustained over 20 years that are less than 10%, and let's depend on less than 10% of the already assessed storage resource base. And that, I think everyone would agree, a very conservative set of constraints already identifies that a target of 92 million tons per year achieved in 2050 rather than the multi-100 million tons per year is imminently plausible. So it's a framework that's very useful, not just in assessing where we are, but also identifying either conservative or more plausible trajectories of where we're headed. Okay, so that's at the very large scale of modeling. The other modeling activity we've done with the UKCCS Research Centre is looking at how the carbon dioxide plume migrates in the field. We're looking here at plan view, so looking down on plume migration, essentially buoyant plume migration of CO2 once it's reached the top of a reservoir and is migrating laterally along a caprock. And everyone working in the CO2 storage, the subsurface aspects of CO2 storage, knows it's a kind of long-standing problem right now to be able to predict precisely where the plume is going, not to any extent that you'd be worried about it at this stage. But if we're going to be achieving gigaton scales of storage, and we're using multiple sites within a region, this is something that we want to have a handle on and get a better handle on over the next 10, 15 years. To bring a long story short, we've identified a kind of leading control of very small scale heterogeneities in the reservoir that haven't been previously considered for hydrocarbon migration, which turn out to be important for CO2. And to demonstrate this, initially, we characterized exhaustively rocks from the Goldeneye field in the Captain Sandstone, obtained rocks from the British Geological Survey core store that look approximately like this. We obtained 40 of them and analyzed them with respect to all of the detailed properties that you need to run an exhaustive centimeter scale reservoir simulation, incorporating now heterogeneities and multi-phase flow properties. So I'm showing here the capillary pressure characteristics as one of the multi-phase flow properties. And this is what had been previously ignored. There are two impacts that are key. So the first impact that you see is on the trapping. So showing here work from Katrin Harris. She's here and has a fantastic poster out in the poster hall. If you just consider CO2 migrating from a lower high permeability region upwards through a reservoir, just crossing a barrier from a lower high permeability region to a higher low permeability region, you'd expect to see a CO2 saturation buildup as it moves, and using conventional modeling of CO2 trapping, you'd see that a certain amount would get left behind, nearly linearly related to the amount that was in place first place. But if you do the full scale modeling, what you see is you actually get these small buildups upstream of the heterogeneity, and this is not a caprock, this is just within the permeable reservoir itself. And what these little enhancements of trapping do is they significantly boost the amount of trapping that's happening within the reservoir. So this is a really fantastic outcome from the perspective of storage security. So Kat has built some analytic models that can rapidly identify how much of this heterogeneity trapping will occur. This is the model of a column in the Captain Sandstone. You see the initial emplacement here, followed by the residual, and this red and black spotted line is the residual with the enhancement. And these light blue lines here show the model estimate you'd obtain if you just use the conventional approach. And what you see is 5 to 15% more trapping due to the heterogeneity. So sorry, there's been something, the formatting lost in the transmission of the PowerPoint. So the second impact regards to the lateral flow that I mentioned in the slide showing the Sleipner and insula migration patterns. And here, what you see is that the carbon dioxide moves through very thin layers of the heterogeneous systems. What we're simulating here is flow of carbon dioxide from the left to the right. We're just showing the comparison between the system when we represent these heterogeneities to the more typical approach when they're not fully resolved. And as a result, the carbon dioxide can move through very thin layers and it can migrate very quickly. The exact enhancement depends very much on the properties of the rock. So this is work by Nelly Wenck and Sejal Menorkar, where we've taken the rocks from the subsurface, either from the North Sea or elsewhere, characterized them in our laboratory equipment that Stuart mentioned, characterized the heterogeneities, and the outcome is complicated. But in short, when the carbon dioxide is flowing parallel to layers. The carbon dioxide migration is enhanced. The relative permeability curves increase, and it's inhibited when it flows across layers. So I don't know if it's possible to just play this animation. Here we show a 2D view of, does anyone have control over the mouse? So if you hover over the animation, there should be a play symbol that comes up. There we go. Yep.
This one here.
Yes, please.
Sorry about that.
Fantastic. So what you can see is a comparison between the heterogeneous system and the more conventional representation. And the plume migrates very slowly, inhibited by these heterogeneities and trapped when it's moving upwards. And then you see the plume hasn't migrated quite as far laterally by the time it gets there, but because of these heterogeneities, it moves so quickly laterally that it catches up to the conventionally modeled system by the end of the simulation. This is the captain, so it's an anticline. If we had just a dipping reservoir, the situation would be even more dramatic in that sense. So, okay, so that's the end. The key takeaways here, the kind of modeling we've been up to, that we should be using models based in the science, engineering, and historical development of the subsurface to represent CO2 storage in energy systems models. It will bring much more plausibility to those models, much more realistic trajectories, which hopefully would put the narrative on the development of CCS back on a more positive trajectory itself. We've spent a lot of time characterizing and incorporating the impacts of small-scale reservoir heterogeneities into a reservoir simulation, and I have identified them as a key control on the amount of trapping and the speed and extent of lateral migration. And all of this has been a real success, boosted by the UKCCS Research Centre that we're continuing on today. So thanks very much.
Thanks. So I'm going to take a couple of questions if there are any. Anybody online, put your question in the Q&A box. Anyone in the room? Anybody got a question? Yeah. Got a microphone, yeah.
Hi, Adrian Topham, Crown Estate. Good presentation, very interesting. I guess what I'm interested by is there was a recent presentation by Chris McMinn at University of Oxford where he's looking at the plume migration in dipping beds, and he's showing gravity dropout of plume migration. Is that something you saw at all, or is that depends on the level of heterogeneity you include in the model, right?
Gravity dropout.
Well, yeah, sort of like a solution dropout, like nodules. Yeah.
Yep. So that's the dissolution itself of the carbon dioxide can actually be dramatically enhanced by the movement of this carbon dioxide through the thin layers. As you can imagine, the interface between the free phase carbon dioxide and now the reservoir water is significantly enhanced. So that effect could, in principle, be boosted by the enhanced dissolution. On the other hand, heterogeneity tends to interrupt this convective dissolution. But yeah, so we haven't focused as much on that as Chris has, but they're all these are all the physics that we're grappling with.
Anybody else? Yeah.
So going back to the beginning, Sam, you're pointing out that the growth rates of CCS based on capture rates were sort of below the levels that we would like to see. And then you go on to show that actually what is possible in terms of the elements of storage significantly greater than that. And isn't the takeaway there that actually the constraints on the growth rate of CCS is not actually the availability of storage. It's other things like business models and so on.
Yeah, the answer is absolutely. And I, didn't have time to go through all the nuances and details of this modeling framework. But one of the really nice things, without getting into the details, you just have to kind of take my word for it at the moment. But on this graph, which is storage resource on the vertical axis and growth rate on the horizontal, essentially, if you see scenarios on the vertical side of these curves, it implies that they're growth rate limited, not storage resource limited. And if the points, and these are each of these scenarios, fall more on the horizontal side of the curve, then you can identify them as storage resource limited. So far, every set of scenarios we've analyzed have fallen well onto the vertical side of these curves, and exactly, they're not storage resource limited.
Okay, I'm going to cut it off because we're late, of course. Thanks very much again, Sam. That's great. And we look forward to getting the slides. So next up, Stuart Gilfillan from University of Edinburgh. Okay, Stuart is a reader now in geochemistry in the School of Geosciences at University of Edinburgh. Did his PhD in noble gases and in CO2 fields and in Colorado, and has stayed fascinated with that sort of thing ever since. So he's now going to talk to us about what he's discovered with CO2 storage and tracing gases.
And some other things. So similar to Sam, actually. So Sam, I'll have to thank for giving a really good introduction to some of the stuff that I'm going to talk about. I'm going to give you a bit of a whiz-bang overview of some of the stuff we've been doing at the University of Edinburgh, which I think, as far as I could best work out from looking through the proposal, is sort of related to CO2 migration and storage as part of the core research programme. As you can see, as per usual in any of these talks, it's from a cast of several other people. It's most definitely not all of my work. I particularly thank Emma, Rory, Chris and Ian, so postdocs and PhD students who are working on this. And I'll talk a little bit more about this nice photo in the background as we go through. So just going back, actually, as I said, really would like to credit Sam for really doing a great introduction to this. So one of the points I wanted to talk about was this paper that we just published just under a year ago about a review of a decade of CCS progress. I've kind of put a question mark on there because what we actually did was compared actually a paper that Stuart wrote in Science about the projects that were proposed back in 2009. And then given it was pretty much 10 years since they'd happened when we put this paper together, we looked at which ones had gone forward and which ones hadn't. And as ever, because I've been trying to do my best to stick to time, I don't have time to go into lots of detail. What I would really encourage you to do, because obviously that's why I'm standing up here to advertise it, is there's the link. Read it yourself because it's got lots more in it than I have time to go through. And as it so happens, what I'm going to focus on is just the rates of growth. And maybe give a similar, not contradict Sam too much, but basically just point out some of the things that we found out, which actually do fit in with Tony's point as well, actually. So relates very well and completely by accident and very fortuitously, because I had no idea what Sam was going to talk about. So very first point, and really important point to point out, is that CCS is operating at scale around the world. The vast majority of that is at the current time for enhanced oil recovery. However, there are still 6 dedicated storage projects, i.e. not doing EOR, and you can see they are storing 73 million tonnes, or have stored, cumulatively 73 million tonnes of CO2 so far. So that's not small change, and that's certainly quite a lot when you look at some of the other projects that are proposed and various ideas of growing small forests or whatever else. If you take in CO2 EOR, we're talking about nearly 500 million tonnes. Some of that does include some of the natural CO2 that I have worked on in the US, but you can see that there on the graph behind me, just showing at that point in 2021 where we are. And as Sam alluded to, the key question really that comes to this in terms of CCS, how is CCS going to realise its climate mitigation potential, is going to be what rate of growth is post now. But the really first take home for this is CCS operates at scale and does so around the world effectively. So that's a key point that people do seem to lose and say it's not an existing technology. It is. So going on to the CO2 storage rates, we have a graph here just showing CO2 stored on the y-axis, millions of tonnes per annum. This is both a review of some of the work that Sam was just talking about, and also some work that Stuart was involved in. And just putting on here the storage rates for historical geological storage, including both enhanced oil recovery and the dedicated CCS. And what you can see is both of those have had a noticeable uptick. So the dedicated storage is lagging behind, but from 2010 sort of onwards, particularly with CO2 to R, there has been a noticeable uptick in the amount, and that is set to continue. What we found when we were looking at what the projects that were proposed and the ones that had gone ahead and hadn't gone ahead, comparing the last 10 years, there's been a big drop and fallout in coal, and then actually a big diversification into other sectors, which is good for industry. And that idea that CCS is just for fossil fuels, again, that really is a myth now, because it is diversified into gas processing, into the other sectors around industrial processes, steel and cement manufacture. Those projects are all proposed into the future. However, one of the things that we did say, and you can see this on the blue line from the Haszeldine plot, is post 2025, there is huge uncertainty. And that is a big problem. I'm not going to go into the details of that, but that's obviously a problem, as Sam alluded to, because we do need that growth rate to increase and to considerably increase. And the problem really with that is that these projects should need being proposed now. And what we found is there is a bit of a sort of blockage in the pipeline, whereby there are planned projects. They should all come on, the ones that we are aware of should come online by 2025 to 2030. But post that bigger scale up into the future, that's really not clear how that's going to happen. And I think we're kind of waiting. It's still a bit chicken and the egg. We need those really big dedicated storage projects to get off the ground and get off the ground quickly to then hopefully capitalize and build more through into time. And just to sort of say a bit of a caveat on this with what Sam talked about, but basically just to show that this is the kind of degree of uncertainty that we currently have based on what we're looking at. So so the graph here on the right-hand side, again, similar CO2 storage up the y-axis, time running up to 2050 on the x-axis. And what we have here is just showing the difference between these future projects that are planned. What we have seen historically up to 2020. So if we just follow the growth rate to 2020 that has happened, we get to about 75 million tonnes per annum by 2050. However, if we increase that by all the projects that are proposed, and important caveat, assuming all of those go ahead, which we know from previous work is not always the case, that we get to about 306 million tonnes of total storage by 2050. So that's quite a chunk. That's a reasonable amount. However, and I agree with Sam on the caveats in this. Various estimates around, and some of these system models have proposed that CCS has to really take a big chunk of this, and it is somewhat unrealistic in terms of how much these are, but this is what is being used to sort of bash CCS to say that it's not potentially going to meet those targets. But really the sum total of that is that the potential is there. It could go on. Again, I didn't have time to put in. There is also another really nice graph in here that goes on to Tony's point that shows that even at this higher rate and even at much higher rates, you're still only getting up towards about 10% of the available global capacity for CO2 storage as we know it now. So it is really not limited by storage. It is really limited by projects. So we need more projects and we need them urgently. That's really the main take home of that review. So moving on to something else, which again somewhat fits into the Sam's talk, is looking at the rates of solubility trapping. So we're basically, again, reviewing things here. This is a data review. We did quite a bit of this during lockdown because obviously getting into the labs and whatever else was more difficult. This is work done by Rory Leslie, a PhD student. And it's obviously this solubility trapping is important for storing the CO2 and provides us with a pretty significant secure trapping mechanism, which is second only to mineral trapping in terms of its security. Can retain up to 10 to 50% of CO2 in the storage reservoirs. And really what we were trying to establish in this study, putting it very simply, is does dissolution, or does solubility trapping happen on injection very quickly and then effectively reach an equilibrium over time, and then it doesn't really matter too much over time as to how long that CO2 is stored? Or does it, do you still get reasonable dissolution to start with, but then you take a long time to reach equilibrium? So the key point on this is, when is that equilibrium line reached? And that's what we were trying to determine in this review of both modelled and analogue studies. And what we found on this, just to put this slightly complicated graph, but effectively just the real sum total of this to say there is a bit of a correlation in terms of the amount of storage duration, or the duration of the storage site in terms of years down the y-axis against the dissolution rate. And what that seems to suggest, at least on the first pass, is that the longer your CO2 storage duration, the slower your dissolution rate appears to be. So indicating, at least on the very first pass, that there is a rapid dissolution rates at the start. And this is calibrated against geophysics from Sleipner, which is the point up the fastest rate up there in the top left. And then looking through into more of the natural analogues, which is work that we're now starting to do, which is taking these particularly US natural analogues where we have data and have long-term CO2 storage, and trying to work out how much CO2 is dissolved in those fields over what sort of timescale, and also looking at how much dissolved on emplacement versus how much is being dissolved through time. And putting that onto sort of an average dissolution rate plot here, which is the fraction of CO2 per year, again against storage duration, does seem to bear that out, that actually there's a non-linear decline in dissolution rates with increasing storage duration. And it does indicate that what appears to be happening is the vast majority of the dissolution is happening, as far as we can see, early on as that CO2 is injected. It's primarily due to the interaction of the CO2 with water. I'd be happy to chat to other people in the room afterwards about how this fits with their work. But that basically shows that early model of sort of fast initial and then a quick equilibrium being reached without a huge amount of change over time seems to be what this compilation of work is telling us. I think that's a really good and really important message for CO2 storage security, which is saying that that solubility trapping is happening mostly on injection and happening quickly, and then gives us some idea of a reasonable amount of security. Not saying that's the case in every single reservoir, and the vast majority of these are based on modelling studies. And as I say, what we're now trying to do is look at the natural analogues to really tie that in a bit more through what we can actually see in the real world. And then the last point I just wanted to chat about very quickly is some really interesting work that's been really exciting to be involved in, which is tracking, going back to what I've been working on for quite a while, which is fingerprinting CO2 and then tracking its fate in the subsurface. And this is working with the CarbFix project out in Iceland. And we're looking here where they're injecting through they're injecting dissolved CO2 and into a geothermal reservoir. They are then showing that mineralizes, so they have reasonable evidence from tracer data that that's then mineralizing in the subsurface, and then they're tracking that in a number of monitoring wells that we were able to sample. This is pretty hot off the press data. This is just showing stable carbon isotopes and stable oxygen isotopes. We know what we're injecting into the system. We can predict what happens with mineralization, which is the grey line on there. And then you can see there, with the CO2 carbon isotopes along the x-axis and the oxygen isotopes on the y-axis. What we'd expect to see if mineralization was a sole change is that plotting along those sorts of lines from the blue down into that direction. And what we find is our data, and this is preliminary data, does plot in a reasonable direction to indicate something is going on, not quite on that line, but is indicating that we are picking up a reasonable signal of up to nearly 40% of that CO2 being mineralized. And that's the first direct evidence from the CO2 itself that's being injected. We have quite a lot more to throw at this, but it does show that hopefully we can do that and watch this space. Very last thing to say about is, I'm not going to show you results, is that we've also got CO2 mineralization experiments, which are ongoing. Stuart's told me that I'm out of time, which is fine. But again, we're also going to do this in the lab to actually see how the porosity and permeability of these rock chip samples evolves through time. And I will shut up there because that'll give us time for questions, but I'll leave up the summary and happy to take any questions on that.
Thanks very much, Stuart. That's 3 talks in 1. So that's good. Any questions? Anybody online? Put your question in the Q&A box. I can read that in the room. Anybody in the room? Put your hand up.
We have one question online from somebody called Clement, who has said, you mentioned that CCS is a working technology in the oil and gas sector. Can you comment on the storage security, as in CO2 leakage rates, that has been observed in that sector?
Okay. Yes. So another study that we did do 3-4 years ago now did look at exactly at that. And in terms of storage security rates, the performance that we have from all of the data, looking at all of the different storage securities and the different trapping mechanisms, implies that it is very secure and can certainly meet the targets that are required. In terms of my own personal use, I've actually developed various different sensitive tracer techniques that could be used for detecting any migration of CO2 from a subsurface storage site, and we can do that at really high sensitivity. So, I mean, in terms of the specific question, I'm not sure quite if that question is to a specific site or not, but we'll do that.
I could just say we put some of that work into context, and the result was something like, out of all the CO2 sites, natural and engineered worldwide, there was a 50% or better probability that 98% of the CO2 will be stored for 10,000 years, which is a good probability, I think. And to put that, and also to put that in context with the seismic reflection people do on Sleipner, I worked out we can detect movement of CO2 outside the box equivalent to about 150 trees in a forest, if you're interested in planting trees. So that's, again, a very good, tight monitoring result. Any questions?
Sorry, that just builds on what I was going to ask. I do apologize. I'm new to this, so I'm going to ask, if I ask a silly question, I do apologize up front.
There's no silly questions.
Could you elaborate on the 6 sites that you suggested that are operational for non?
For non-EOR, I couldn't list.
Then building on that, how can we use that to validate the modeling, or are you guys doing that already? The data from those sites.
So, I mean, I can list a couple of those sites. So, I mean, Gorgon in Australia is the biggest dedicated one, which has been somewhat controversial and took a while, as these things tend to do in terms of new first-of-a-kind projects to get up and running, but is now injecting significant volumes of CO2. There's Decatur, which I can never remember how to pronounce. I think that's how they pronounce it, isn't it? But I'll defer to Sam, who knows. Or Decatur, isn't it?
Decatur is,
that's right. Decatur. Right. And I'm just trying to think of and obviously Sleipner, Snøhvit, which are the 2 original ones. So the Sleipner in the North Sea since 1996, Snøhvit since 2012 or so, wasn't it? And then Boundary Dam, which was the world's first coal CCS plant. And then Quest, which is the Shell one on an upgrader. So that's got 4, at least 5, 6. That is 6. Yeah, so that's all of those. And in terms of the monitoring of those, so yes, all of those are being very carefully monitored, mostly by the operators. We've also, Sleipner being operating since 1996, that's been subject to various different seismic surveys through time. It's been done, it certainly was done for the first 10 years, every couple of years. They ran more seismic surveys on it and can map the sort of plume, and they're actually using that to get the dissolution rate in that field. Quest as well, they have quite sensitive monitoring techniques. the one that I've forgotten how to say again, Decatur, has also been very extensively researched. And so all of these, if you are interested, I'm happy to send you more information on that afterwards. But there's plenty of research that's been taken both by industry and by the research universities as well. No problem.
Quick one.
Calfix 2, thanks. Calfix 2 and your data showing some mineralization. So you've been sampling since 2018 there. Are you able to back out any of the kinetics around that mineralization process from that data set?
So I'll be honest, we're not looking in great detail at the kinetics. So most of the work that's been done has been done by the Carbfix group themselves, and they have been looking quite extensively at the kinetics and the modelling in terms of the geochemical modelling of what's going on. Our work, just to be clear on that, is really focused on tracking the fate of the CO2 itself, because what they've used up until this point effectively is a mass balance method with injecting artificial tracers, and we're just trying to see if we can actually use the inherent tracers within the CO2, both the stable isotopes and the noble gases, to really track the fate of the CO2 itself. Again, just for the future, being that you don't have to inject additional tracers into that system. But in terms of the kinetics and things, there have been a couple of good papers actually that have come out in the last year or so from the modelling group, which I can certainly send to you if you're interested, because they have been working quite extensively on that.
Yeah, I'm going to try to check is Adam Butler? Yeah, I thought that must be you, right? That's good. So I don't know Adam from Adam, as it were. So Adam from University of Cambridge, first degree at University of Cambridge, went to Imperial College, back to Cambridge again now in Earth Sciences and Environmental and Industrial Fields. And whenever I read a CV like Adam's, I think how pathetic you are, Haszeldine, because Adam just does, aircraft wing fluid flow stability, and then just decided to do a bit of CCS and flow as well.
Yeah, hi everyone. I'm Adam. I'm a postdoc working with Jerome Neufeld, who unfortunately wasn't able to make the meeting today. So he asked me to come and talk to you about, give a very quick overview about some of the reduced order modelling that a few members of the group have been doing recently. And so I thought I'd start with talking about work done by Lawrence Coaten, who was a PhD student a few years ago on the Sleipner project, which we've heard about a couple of times today so far. And this has quite a few nice properties as a reservoir, in that it has a very thick formation, about 300 meters, and a very high permeability and porosity. And the seismic surveys we just hearing about show very clear reflections of the CO2 you can see there on the left. And if you pick out those various different layers, it forms these 9 layers, famously for Sleipner. And Lawrence went and took those seismic measurements and looked at the interference patterns between different reflections of the CO2 and was able to pick out the CO2 thickness for the top layer of the reservoir over time, which you can see here on the left. And the interesting feature of that is that it doesn't just follow the topography set by the top of the reservoir. There's this long north-south channel to the CO2 plume, and that's therefore caused by some heterogeneity in the properties of the reservoir. And so what he set out to do was trying to model and infer what was causing that behavior. And so, is that going to show? Oh. Those should be animated, unfortunately not. So a quick summary of how this kind of model works is that the CO2 flows based on Darcy's law, and because soon after injection, the horizontal length scale is going to be much longer than the vertical length scale. That means you can assume that flow is predominantly horizontal, and you get hydrostatic pressure in the fluid, and then you vertically integrate across the reservoir, and that gives you a volume conservation equation shown here in the box on the bottom left, which is now only 2-dimensional rather than 3-dimensional. And so this is a much simpler thing to solve numerically than a fully 3D simulation. I guess aren't working. And so Lawrence went away and applied this to those measurements he'd taken from Sleipner. And based on these seismic surveys, there's the remains of an old riverbed which is influencing the behavior of the CO2 plume there. And just with a simple model that has 3 parameters to it, the width of the channel, the permeability of the channel, and the permeability of the background, he was able to reproduce the behavior of the CO2 plume in that top layer. And the kind of key benefit of this reduced order model approach is that you can take these kind of simple models and run lots of simulations in the time it would take to run one full 3D simulation. So that allows you to find these best fit solutions and also give measures of how good a fit it is and kind of quantify the uncertainties and the parameters involved. On the other kind of end of the spectrum to Sleipner is Insala, which has correspondingly very thin formation, a low permeability and a low porosity. And what people have seen at Insala is that over the 3 injection wells involved, satellite measurements have found detectable surface uplift of each of the injection sites. And so this is due to the increased pressure due to an injection. And in order to model this, you're going to have to take deformation of the reservoir into account as well. And so I've been working on an extension of the kind of model that Lawrence used. But now this includes the flow of both the CO2 and the ambient brine, shown on the left in blue and green respectively, the deformability of the reservoir itself and the deformability of the overburden, which is giving you that observable surface deformation, and then the topography of both sealing layers of the reservoir. And the interesting thing from this is that during injection, the deformation signal you'll get is going to spread out much faster than the CO2. And so if you can measure that deformation signal, then you're going to be able to infer things about parts of the reservoir that CO2 hasn't yet reached. And so I've gone and applied that to one of the observed uplift profiles over the well KB501 there. And just with a simple model for the kind of known fault structure around that well, I've been able to reproduce the observed uplift profile you can see here on the left and put some values to the permeability and width of the damage zone related to that fault. And I do have a poster about this if you want to discuss this in more detail. I'd be happy to talk about this in the drinks break. So both of those we're talking about large scale heterogeneities and permeability of the horizontal. Obviously, there's also variations in the vertical direction across the reservoir, which you can see, for example, in this picture of West Bay cliffs in Dorset. And so kind of related to the question we had earlier, Kieran Gilmore, who's a PhD student who recently finished in our group, looked at a simple model of dissolution of CO2 fingers along high permeability channels in a reservoir, and CO2 dissolving into the surrounding ambient brine. And he went and applied this to the Salt Creek field experiment in Wyoming, and found that with kind of reasonable parameters for this situation, you can get up to 10% of the CO2 can be dissolved in the first year during injection. Kieran also has been working on an extension of Lawrence's model to include residual trapping, where as the CO2 recedes from an area, part of it is left behind due to surface tension effects. And he's been working with folks at UKCCSRC to apply this to data at Otway. As you can see here, fitting to observe measurements from seismics. And finally, Graham Benham, a postdoc who's recently left our group, has done some really nice work on incorporating the kind of ideas that Sam was talking about earlier in terms of capillary entry pressure and saturation, matching that to heterogeneities, vertically spaced heterogeneities in the well. And it's found that generally the CO2 is going to be promoted into regions of larger porosity and permeability and smaller capillary entry pressure. And he went and looked at a variety of different permeability structures that you kind of typical representations for geological settings. And by studying, running thousands of different realizations of this, he's been able to look at the statistics of the behavior. So, for example, how quickly is the CO2 plume going to spread compared to the purely homogeneous case? So that was quite a quick overview of all the different things that we've been working on. But hopefully I've been able to demonstrate that these kind of reduced order models are still able to incorporate the key physical processes that we want to study. But because you've been able to reduce the kind of the dimensional convention of the problem, they make them ideal for inverse modeling or forecasting and uncertainty quantification because they're much cheaper to run numerically. I went quite quickly there, but I think I'll just stop there. I also have a list of references if anyone's interested.
Thank you very much. Unluckily or luckily, you've left yourself lots of questions. So again, anybody online, put a question in the Q&A. Anybody in the room, please put your hand up. Stuart.
So thanks for a nice overview of all the different work. I mean, it's good to see the models fit. I'm just wondering what are the most important sort of key physical processes that you can, how simple can you make it, I guess?
I guess Lawrence's approach is kind of the simplest way you can. If you've got something like Sleipner, where you can kind of ignore the ambient flow, you can ignore the base of the reservoir, then all it is topography and variations of permeability. Mm-hmm. So that's kind of the simplest one you can hope for, and it managed to work really well for that. For other reservoirs, for example, like inside, you have to take other things into account. But again, I guess it depends how fine a resolution you care about modeling down to. But the more physics you can incorporate, the better.
This is a slight follow-up one. How closely does it match the rates? I mean, it's obviously getting the direction. Is that matching the rates pretty much as well in terms of?
For instance?
Well, for Sleipner or Elsala or the other ones?
Yes, I think they both do match the spreading rates and the how do you want to quantify the injection rates.
Yeah, cool. Thanks.
Question?
Great, thanks very much. Thanks for that. So other question, and it can be kind of open also to you, Stuart, is about the dissolution trapping. And you're showing really nicely that you can have very significant dissolution trapping in the near term. But, as we've seen with the mineralization, and it's very difficult to, right now, say whether this has actually happened in a field setting with the project. So I'm just wondering, what can be done to push these kinds of models and results towards observables that you could include in policy, for example, that would allow dissolution trapping to be included in project management plans or project verification plans. And the flip side is, if we haven't thought about it, I mean, these ideas have to come from us. And so I'm also partly pushing the idea that if you haven't thought about it, it's something that should be seriously thinking about, especially if we can see 10% dissolution, within the first year of the project.
Yeah, that's a very good question. I don't have an immediate answer to that, but yeah, it would be great to have some clear observables for what you can take away with that, what you can measure.
So, I think it's a great question, Sam, and I think it is a great call to action as well. I mean, my personal opinion on this is I think that, we've got good heterogeneity modelers, geochemists in the room. What I always find a little bit disappointing is we don't seem to have been able to persuade the funders, and I think it is really on the funders that we should all get together and actually work on a particular project. I mean, particularly around the geophysics and the geochemistry, and how that then fits into some of the work that you've been doing, particularly around the modelling side of things, I think would be really, really powerful, and integrating that all together. But it's really tricky to do, just getting everybody into the same project. And we tried to do it with Otway to an extent. But again, that was, particularly the geochemistry, was sidelined because of access for fluid sampling. And I think what we've not really done yet is have a real project where they've put as much geophysics in as they did in the Otway, with some geochemistry to calibrate it. And then you could then take that and model it through. And I think that's really what we should try and do somehow or other. And if that's something we can do in the UK, that would be great.
But we can do anything in the UK, really. But to put that in a slightly different way, coming from the chair's privilege, then does this mean that anybody with a commercial project trying to rely on seismic mapping 5, 10 or 20 years after they've injected is going to be 10, 20% short of detectable CO2 because the CO2 is dissolved? So you're going to have questions from the regulator about where it all went.
Similar ways of
Anyway, you're off the hook. Back to aeronautical engineering. Okay, so last but by no means least, John Williams from the British Geologic Survey. And BGS, as we know, have got a very large and long-lived programme on carbon capture and storage, having been pretty much first into doing it in the UK geologically. And John has been working on lots of things about analogues, about the CO2 underground labs. So I've no idea what he's going to tell us about, but it'll be something to do with that. And if I could just get this to go on to... There you go, that's you. Oh, it's John Williams.
Thank you, Stuart. Hello, everyone. Okay, so I'm going to talk about a variety of things. It's going to be a bit of a whistle-stop tour, really, but I want to talk about some issues around large-scale storage. In particular, the way that pressure propagation can affect storage capacity and a number of other issues. I'm going to talk about some modelling we've done on a regional scale for the Butler sandstone saline aquifer in the southern North Sea. Then I'm going to point out a few potential issues with that model and highlight a few pieces of work we're doing to address those before segueing into the topic of storage testbeds and what challenges these might be able to address. So first of all, pressure propagation. So we know that large-scale storage is expected to result in widespread pressure increases, which is especially true in saline aquifer formations such as the Butler sandstone. So the Butler sandstone is very important strategically for the UK. It's a potential storage target for several industry-led projects. It's namely of relevance to the Teesside and Humber industrial clusters. And it's also of relevance to 3 of the current storage licenses in the southern North Sea. And I think whilst storage operators can probably tell us an awful lot about the reservoir properties at their individual storage sites, I think it's fair to say that taking a regional view, reservoir properties still remain rather uncertain for this potential storage reservoir. So here I'm showing some results from some regional reservoir simulation studies. So in this work, we've taken some predicted industry CO2 capture profiles where we have a total of 600 million tons of CO2 captured over the period. We're basically injecting this into 3 large structural traps, these known as Endurance, Closure 40 and Closure 36. This area here is quite a large volume. It's some 80 to 100 kilometers in length there, to give you an idea of the perspective. Now, what we see here from the saturation plots, so these colored blobs, these are essentially the destination of the CO2 plumes at the end of the injection period. So we see that these are nicely trapped within the target structures. But what I'm more interested about for the purpose of this talk is the right-hand plot, which shows the pressure increase at the end of the injection period, where we see the pressure increase is really quite widespread. It's highest there in the center of the model, in the vicinity of the site known as Closure 40, where it reaches pressure increases of almost 100 bars. So really quite significant and really quite widespread across this whole region. We've pumped those model results into a regional geomechanical model. So here I show a cross-section illustrating the vertical strain results. This section extends from the Endurance structure over to Closure 40, and then finally over to Closure 36 on the right-hand side here. And basically what we're showing here is that we've got a fairly limited geomechanical impact with only minor elastic strains. So this blue band through the center of the model here, this is basically dilation occurring in the reservoir as we pressure it up, and we get some contraction strains that somewhat counteract that. But the main result is that the halite caprock does remain stable despite some local tensile failure in the reservoir in the vicinity of the injection sites due to the cooling caused by the injection of cold CO2. So if we look at what this actually means, then what's actually happening? Well, this plot here shows the same line of section, but it's colored up by basically the surface uplift. So this is the movement we would expect to see at the seabed as a result of the model strains. And now we see this is at its maximum above Closure 40, where we saw the highest pressures occurring in the reservoir. And we're seeing displacements of the seabed here, positive displacement of some 12 centimeters in this part of the model. Now, if we look at the map here, this shows the extent of the surface uplift. And you can see, again, it's pretty extensive. It does relate to the underlying pressure response. And we can see that you obviously got some highs there in at the location of the various injection sites, but we also see some relation to the subsurface structure, which is quite interesting. And the reason I've showed this here, the black polygons you can see are basically the locations of current and planned wind farm developments. So I just thought it was interesting to show how this kind of regional pressure response might potentially interact with other energy transition infrastructure. So that's just a point of interest there. So I've showed you some modelling work, and now I'm going to point out one of the limitations, and we've had some great talks already about fine-scale reservoir heterogeneities. So I'm ashamed to say that in this model, we have ignored the majority of them. Which I think is actually fine for the purposes of modelling the pressure, but would mean that the saturation distributions of our CO2 may not be as accurate as we would want them to be. But anyway, I'm focused on the pressure for now. But our current model basically assumes a highly simplified distribution of porosity and permeability across the region. You can see the challenge. We've got this huge area of storage reservoir, our saline aquifer. We've got basically a fairly sparse distribution of data points with which to characterize accurately these fine-scale heterogeneities that have been talked about earlier. But basically, the data that we do have suggests that there may be two areas of note. We have the southern area with higher porosities and permeabilities, and then the rest of the region here. The orange colours have somewhat reduced porosity and permeability. So I won't go into the detail, but they're basically delineated in this model by the extent of a phase reversal polygon that we can interpret on the available seismic data. So it's quite a simple approach. It's somewhat pragmatic, and it sort of suits our purposes of looking at this regional pressure response. But despite that, it's pretty clear that there is a lot of uncertainty here. So we really need to get to grips with what are actually the controls on reservoir quality and distribution across this sandstone unit. So we've undertaken a series of more detailed studies, which I'm just going to blast through now in the next couple of slides. But the intention of these is really to work out what might the flow implications be, and do the current model assumptions capture the bulk reservoir behavior of this system for the purposes of modelling this pressure propagation. So first of all, we've undertaken a study to look at the stratigraphic architecture of the Butler sandstone. So in formal kind of stratigraphic nomenclature, the Butler sandstone is just that, it's the Butler sandstone unit. However, if we look to the literature in the Netherlands and in North Germany, there is an established stratigraphic nomenclature. So what we wanted to do was to see whether we could correlate this across to the UK. And in short, it's kind of possible, but it is a bit more challenging because the UK extent of the Butler sandstone is actually highly sand prone. Hence, the subdivisions are difficult to distinguish because we don't have these thicker shell packages with which to distinguish the various subunits. Much of the bunter in our sector, especially in our area of interest here, is actually eroded beneath the hard decks and disconformity. So the upper sandstone units present in neighbouring countries, these kind of depth-first sandstones, these are actually absent in most of our study area. They're only present in the southern extent of the UK sector. So what we're actually looking at here is these lower units, the Vogelhausen clay siltstone and Vogelhausen sandstone units. So that's quite that's useful information that isn't particularly represented in the formal stratigraphy to date. We've also undertaken a regional sedimentological study. So we've done a lot of core logging. We've developed detailed descriptions of some 850 meters of core taken from 15 wells, logged at a fine scale of 1 to 20. So we've generated some Fashes logs, correlation panels, depositional models, and Fashes association maps. The system is basically a terminal fan setting, but there is quite a bit of variation within it. So I'm pleased to say that we're in the process of writing this work up, and quite a lot of the data will actually be made available to the community via the UKCCSRC data archive. To complement that, we've undertaken a petrographic study, which is a bit of a shotgun approach, really. You can see the little black triangles there showing the distribution of the wells that we sampled. So we've got 81 samples from 12 wells, which is quite a nice distribution. However, we're sort of missing that really tight resolution in the vertical sense through this kind of almost random sampling sort of sample distribution. But the aim of this study was to look at the depositional and diagenetic history of our system and to attempt to relate our observations to controls on porosity. So I've shown a few of the highlights here. I don't think I've really got time to go through these in detail, but basically we've got things like early spheroidal carbonate nodules that potentially 4 millimeter scale barriers to flow as they're preserved in thin laminae. And you know, this is one of the most important aspects, really, where we have these early anhydrite and halite cement phases, which basically preserves the uncompacted grain frameworks during burial. So it's basically preventing compaction, which can lead to difficulties in predicting the porosity of the system. Then there's other things going on, and of course we've got the later halite and anhydrite cementation that occludes the porosity, in which we can see also on the seismic data around the endurance site. So again, this work will be written up, and quite a lot of data will be made available in due course. So I'm just going to segue now into talking about subsurface test sites and what they can tell us about storage, and particularly large-scale storage, and how to upscale it. So really, quite early on during this phase of the UKCCSRC project, we came up with some initial concepts for a subsurface facility comprising a single deep well at the Cheshire site, which was developed alongside the UK Geoenergy Observatories project. So we got quite far with the designs, and these were reviewed and costed. However, unfortunately, the CCS component was not taken forward to the planning stage, which was a bit disappointing, but we moved on. So subsequently, we developed a new concept for a research facility that would be located on the east coast of England, with the express aim of supporting implementation of storage in the southern North Sea and the Bunter Sandstone. I remember presenting some thoughts on that at, I think, the last in-person biannual in Edinburgh a number of years ago now. But anyway, that's what we sort of developed with support from the UKCCSRC, and this formed the basis for an initial capital funding application, which was submitted to NERC. And then it's gone off and it's grown a life of its own, and it's ended up eventually resulting in the development of a science case for a new dedicated research facility with the aim to assess the challenges in long-term CO2 storage. This is known as COS Lab, and it was mentioned earlier in the plenary session by the chap from the UPSRC. So as part of that, I think many of you here in the room participated in a extensive stakeholder consultation process, which basically informed the development of that science case. Now, I just want to highlight on this slide a few of the thoughts, focusing on some of the commercial and industry stakeholders. So essentially, the commercial and academic communities did raise some pretty similar challenges broadly. However, I'd say the industry did tend to focus more, unsurprisingly, on assessing operational questions and the testing, verification of novel tools, methods, and cost-effective MMV systems. A few of the operational considerations that industry thought a subsurface geolab could address included the consequences of variable supply rates, different CO2 streams, and periods of intermittent injection, and the impact that has on flow assurance, injectivity and storage efficiency. And also the commercial stakeholders were generally fairly keen for such a facility to address challenges that they would never knowingly undertake in the field at their actual CO2 storage sites, such as, for example, pushing the systems and pushing the infrastructure towards operational limits, which could provide some really valuable insights, but obviously you wouldn't do at an industrial site. So I'm not going to read through these in detail, so I'll probably just leave this up here for you to peruse. But I'd recommend reading the COSLab science case report, which should be made available in the next few weeks, I believe. I'd recommend you read that. But anyway, these are some of the science challenges that are identified in that. And basically, I'd say they probably represent the CCS community's view on what subsurface geolabs and deep borehole research arrays could potentially address. So with that, I'll thank you all for your time and happy to take any questions.
Thanks very much, John. Good. Take the time as well. Questions, anybody?
Thanks for that. I was wondering how much is known about compartmentalization in the Butler at this stage, and if any new information arose from the study that you've been doing.
It is a great question, actually, Sam. Thanks. If I can go back. So the sort of the BGS view has always been that this region here outlined in the red box represents a kind of single structural compartment. It's bound on three sides by major faults and salt wall features along here and also to the south. So that sort of looks like a fairly closed compartment, if you like. And there are other kind of structurally, sort of regionally compartmentalized areas of Butler as well. So sort of west of the large Dowsing fault zone and to the north of the kind of Flamborough Head kind of fault system here, that may be another system. This may be another system. But yeah, there is quite a lot of uncertainty about that. In terms of large kind of seismically sort of mapped structures, so that kind of makes intuitive sense. But again, there's the question of do you suddenly lose permeability up here, for example? I don't think so, but these are the kind of issues that we need to look at.
So let's just partly follows on, but on your wish list of menus, and you didn't have anything much about fault zone permeability along a fault in the reservoir, rather than a regional case. Because if you look at other bad waste geolabs, then they'll spend 10 years measuring permeability of a fault, for example. Anything on that?
Yeah, so you're right. I think it wasn't explicitly listed in that kind of challenge list, right? But yeah, I think I remember from a few of the discussions I was involved with as part of that consultation process. A lot of people did ask about faults, and there was a bit of talk about kind of controlled leakage experiments and things like that. It didn't tend to be the consensus view that was a primary thing to focus on.
And where will we get the COSLab report when it's?
I'll probably defer to Maxine, actually, who's nodding at me furiously.
Very quiet so far. Max. Where will we? So the COSLab report, science report, will be published in the next month or two. So do we look on the BGS website, or do we look for an UKCCSRC announcement, or what do we do?
All of those out. You have to go through the various approvals, all the various comps people. The focus is not to take longer than I would like to be able to say. I would like to say in next month.
Yeah.
But I've got my fingers crossed behind my background.
Well, in the nicest of ways, but as long if you just let us know in UKCCSRC, then obviously that just means we know not to worry that we'll emerge through the process.
I think what I'd like to say is the really and helpfully, usefully everybody contributed. It's not just from the UK, but beyond the UK, pilot sites and other projects around the world. So it was really a great strength. Our science case is really very strong because of the great input from people such as yourself and Stuart. I know you're contributed, for example, an industry, and that has made the science case really strong.
Good. Good. That's what community is all about.
Yeah, I'd just have to add to that. I think the science case itself is an incredibly useful outcome of that particular project. So it's well worth the look at.
Thank you very much.